So here we are again. This is part 3 of 3, and this is the end of the questions which I'd set you, questions 21 to 31. I've rewritten the end of the paper which I'd given you yesterday, and this now is tidied up at the end, and I've chopped a couple of little bits out after rereading some of the questions. So let's have a look at this right now. I'll go through this fairly briskly. So question 21 asks about power factors. So I've pre-written my answer. It's not perfect, but it'll do. A power factor occurs when an inductor or a capacitor is connected to an AC supply. The inductor makes the supply current lag the supply voltage. They are not in phase, so the circuit has a power factor. A large power factor, for example 0.7, makes equipment more expensive to run. Okay. So just a quick reminder, an inductor produces a lagging power factor and a capacitor produces a leading power factor. So they are opposites. So on to 22, power factor correction. Power factor correction means trying to bring the supply voltage and supply current back in phase. For an inductive circuit, connect a capacitor across its supply terminals. That's really short and sweet. You may wish to amplify a little bit more on that, but it'll do for now. Okay, so the next question is still about power factor, and it's question 23. And you're given a little bit of information, 2.5 kVA and 2 kilowatts. So power factor equals, remember this formula, kW over kVA. Let's put the numbers in. The kilowatts was 2 kVA, 2.5, and if you put that in your calculator, you'll come up with 0.8. Okay, nice and easy. Part B. It's possible that in an exam this may happen to you. You're given 10 kilowatts, and you're also given 40 kVAR. So on this one, you haven't got the information you need. So I'm going to sketch really badly, doesn't matter, the power triangle. Kilowatts always goes at the bottom, so 10 kilowatts. This is 40 kVAR, 40 kVAR, and it's kVA that we need to use that formula to find power factor. So this is Pythagoras. So very quickly I'll scribble it over here. kVA equals the square root of 10 squared plus 40 squared equals 41.2. So that's kVA. So we now have this number and this number, and we can do the power factor. Magic formula, power factor equals kW over kVA. I'm about to run out of page here, so I'm going to work across. kW is 10, kVA 41.2, and that comes to 0.243. That's done. So there are two parts to this. This was part 1. Part 2, so part 1 was finding power factor. Part 2 was finding the phase angle. Phi is cos to the minus 1 of that number. That was power factor cos. So we do 0.243 there. Put that in your calculator and it comes to a huge angle, 75.9 degrees. Okay, swiftly on to 24. Right, so 24 is about a star-connected transformer. You've got a line voltage of 415 volts. What's the phase voltage? The formula you need, VL equals root 3 VP. You're going to transpose it. VP is what you want, leave it there. Move the root 3 under there. So VP equals VL over square root of 3. Put your numbers in. 415 over root 3 equals 239.6, which some of you may recognize as about 240 volts. Okay, so there was a part B to this question, and I hope I've left myself enough space here to do it. It was about a delta connected transformer, and that VL is 400 volts, IL is 50 amps. Determine the phase voltage and the phase current. So first thing, in delta, VL equals VP, and we were told that one of those was 400 volts, so they're both the same. So that's what you need to do. Tell me. Correct. The next bit is finding the phase current. The line current. Apologies, it is the phase current. So from the formula, IL equals root 3 IP. This is what we want. Leave it on the top and transpose. The root 3 goes under the IL. So we'll end up with IP equals IL over root 3. Put your numbers in, I'll work across, apologies. IL was 50 over square root of 3, and that comes to 28.9. Righto, moving on. Just going to put my hand over this. On question 25, it says a 400 volt supply feeds a star connected load. This is the star connected load. Once you're told that 400 volts is feeding it, if you wanted, you could just put on there and on there 400 volts from there to there. So if you've got 400 volts across two ends of a star, that's 400, then this is 230. What I've done is I've literally put the supply transformer in, and it will do something like this. There we go. So you're going to have 230 volts here. You would have 400 volts there. But that 230 volts goes all the way along here. They're in parallel. So we've got 230 volts across that load, and the load was 20 ohms. At least I think it was 20 ohms. 20 ohms in each phase. Right, so what you've got to do now is figure out the current here. So that's going down an individual branch, which is a phase, and we can work it out using Ohm's law. IP equals, you've got the voltage and the resistance. Should be easy stuff for you. I equals V over R. Put the numbers in. The voltage across there is 230. The resistor is 20, giving you 11.5 amps. Okay. So that is important. Just check that question, because you've got to find the phase and line currents. Tell me, in star, IL equals IP, and we've just found it as that, so equals 11.5 amps. If you don't tell me, you don't get the marks. Okay, so that's that bit. Let's get that one out of the way. That takes us to 26. So 26 has asked you to do it graphically. We're finding neutral current. You could be asked to use the formula. I'm not doing the formula here. It's in your notes. Check it out, learn it, and these questions do occur. So we've got to find the neutral current. So you're going to use a ruler and draw accurately to scale. I1 is 30 amps. I'm going to do this freehand. So 30 amps, you're going to do a line probably 3 centimeters long for 30 amps. So that's your first phaser. From the end of it, which is right there, you very carefully and accurately place your protractor on there, and you're going to measure around. So it's going to be upside down like that. There's naught. You're going to measure around 120 degrees. And at 120 degrees, you're going to do a line down there. And we want it to be 75. That's I2. So you measure 75. There it is. So that now scribbled in untidily. Oops. Sorry. 75 amps. That ends there. And we're going to put the protractor on the end of that. Right on the end there. So your centre of your protractor is there. Measure round 120 degrees again, and we sketch your line up there. And the final one is 50. So you measure 50 up here. There it is. So that's 50 amps. And the difference from where you started to where you finish is the neutral current. Measure it with your ruler. And whatever scale you've used, you need to remember. Okay, and made a mistake here. I haven't got the answer. I'll see if I can sort that out for you a little bit later, and I'll post that onto Teams for you. Okay, so that is the neutral current question. That takes us all the way up to question 27. So question 27 is an AC power question. P equals VI cos phi. I'll come back and talk about that in just a second. So you're given the information, nice and simple. 230 volts. The current in the question was 8 amps. The power factor was 0.75. Multiply them all together and you get 1380 watts. If you preferred, you could have written 1.38 kilowatts. I don't mind if both answers are correct. Let's just talk about this for a second. It's very common to be asked to find the current, and they'll give you power, voltage, and the power factor. Or they could ask you to find the power factor if they give you power, voltage, and current, whatever. So my point is you're going to have to transpose it. So have a think about that. And that was 27. On to question 28. I've rewritten this question. It was getting a little bit out of hand. So let's just try and fill some of these in quickly. Breaker types. Type B is, let me do it in a different colour. No, I haven't got a different colour. Type B is mainly for domestic, and it's mainly resistive loads. Or you could have said low inductive loads. So type C is for small inductive loads. Fluorescent lights, small motors and fans, that sort of thing. Type D is for large inductive loads. Okay, so on to the fuse types. I've shortened this, I just made the question far too big. So part B, a BS 1362 fuse, you will find a BS 1362 fuse inside one of these. So that's the sort of little fuse that goes into the standard 13 amp plug top. Let's put my paper back. The next one is, let's write that in, 13 amp plug top. So the 3036 is what we call a semi-enclosed rewirable. You'll find that in an old customer consumer unit. And just to show you what we're talking about, this is what we're talking about. This is a semi-enclosed, so you can actually see the fuse wire in the gap there. This is old technology, typical of my house, built in 1978. So this is old. Right. So BS88 fuse. This is a special fuse usually used for protecting motor circuits. Righty tighty. So on to part C. I should have had this covered up, but the final part of that question is about explaining the operation of the magnetic and thermal parts in a circuit breaker. So let's do this. First of all, let's look at the magnetic part of the breaker. Just bring that over there. Okay, so in the magnetic part, a coil is used as an electromagnet to operate the tripping mechanism. The load current passes through the coil. When too much current flows, a plunger is pushed or pulled to make the breaker trip. This tends to be fast operating, so a sudden high current causes a trip. The second part of this system is the thermal element, so thermal. This consists of a bimetal strip that bends when it heats up. The load current passes through the strip, so the higher the current, the greater the bend. This is slower to react than the magnetic element, so it allows a high inrush current to pass without tripping the breaker. Okay, so I'll say no more about that one. Let's move swiftly on. To question 29. So looking at some motors, let's pop this back in there then. So I've changed the way I've numbered the question. I've no idea what EAL or any exam board will do to you. So instead of going A, B, C, I've gone 1, 2, 3, 4 using Roman numerals this time. So part 1, 2, 3, 4. So the first part, state what makes a three-phase induction motor begin to turn. Well, it's the three-phase rotating magnetic field. Part 2, state two advantages of a three-phase induction motor. There are many, but a couple of the simplest ones are it is simple, rugged and robust construction. As a result of that, there are few moving parts, so it needs little maintenance. There are other factors, like, for example, it doesn't have brushes, therefore it doesn't spark, so it could be used in an explosive atmosphere. For example, there are others. So part 3, sketch the diagram for a, which one was it? It was a capacitor start motor is what you have to do. So I'll try and do that at high speed now. So hopefully this won't get too untidy. So all right, so we have single phase AC supply. This represents the rotor. This is the main run winding, and this is the auxiliary or start winding. This is the capacitor, and this is a centrifugal switch. Okay, so all you're asked to do was, from my question, was do the diagram, which we've done. And in part 4, it says name two other types of single phase motor. Well, I've listed the whole lot, and I've put split phase, shaded pole, capacitor start, capacitor run, plain capacitor, and universal. So those are the other types of motors, and we'll move on from that. So we're right up towards the end of this little video clip. So I've moved on to DC motors on question 30. first of all sketch a series motor. Oops. So a series motor, nice and easy. From the positive of the supply, we have the field, then we have the armature, and then it comes back. So this is the armature, and this is the field, and they are in series. So there's a series motor. Shunt. Shunt means in parallel with. DC supply, and here is the field, and here is the armature. And a compound motor. A compound is a mixture of both series and shunt. There are a couple that you could do. I'll just go for the short shunt. So a compound motor, there would be two fields. This is the series one, and this is the shunt field, and this is the armature. Swiftly moving on, part D. What is commutation, and what does it mean to a DC motor? The word commutation means switching, so we're switching, constantly switching something. So if you read through my explanation, in a DC motor, the commutator ensures the current passes through each conductor in the same direction when the conductor is in the strongest part of the field. So DC motor, the commutator ensures the current passes through each conductor in the same direction. That's why we use it. Okay, so I think this is the last one, 31. So which type of motor starting method would provide a gradual speed up and a gradual slowdown for a very large motor? Well, in short, you want to use either, you will call it electronic start. Another name for that is soft start. Part B. What type of motor would be used with a rotor resistance starter? Well, that is a wound rotor motor. In case you're not sure, that's the one with slip rings. And I've actually, if I just hide the answer to that, I don't know if I can get the diagram on screen, I haven't got it to hand. But question 31 asks you to explain how the system starts when you've got a motor starter like the one shown in your photo. So I've tried to bullet point it. Let's have a look. So it's a direct online starter. So to start the motor, close the isolator too. That's the first thing you do. That puts power onto the system, but it's not running yet. Press the start button, which is 3 in the diagram. This energizes the contactor coil 4, and the contacts on this will now operate. This closes the contacts, which are numbered 5, putting the supply onto the motor so it runs. So that's what you're expected to do, just explain the diagram which I'd given you. Okay, that'll do for now. Hopefully I'll upload this later. Bye.